Guys, we are going to talk about Saytzeff rule in halogen derivatives. Alright, now there is something there. Now, prior to getting into this, let's read this out. Greater the number of alkyl groups attached across the double bond, product would be more stable on dehydrohalogenation reaction. Initially, let's try and understand dehydrohalogenation reaction, and then let's come to Saytzeff rule and then check out which of the product would be more stable. Alright, okay. So let's try and understand dehydrohalogenation first. Hydrohalogen, hydro, H, halogen, fluorine, chlorine, bromine, iodine, halogen. So hydrohalogen is HCl, HBr, HI, HF. These are all hydrohalogen. Now we are talking about dehydrohalogenation. D is removal. Removal of hydrohalogen is dehydrohalogenation. Fine, understood? Okay. Now whenever we talk of dehydrohalogenation, means what? Means we know this reaction. Suppose I take, say, HCl, hydrohalogen. I react it with KOH. Acid-base neutralization reaction you are aware of. So it would give KCl plus H2O neutralization reaction. Alright, we know that. If I want HCl to be taken care of, I can use KOH, sodium hydroxide, potassium hydroxide, and all those alkali hydroxides would take care of hydrohalogen. Alright, a similar type of things happen over here. Now let's look at this molecule. This is 2-bromobutane. 1. So methane, ethane, propane, butane. Now we have got to give, as per IUPAC, we have got to give least number to this. We cannot number it 1, 2, 3, 4 like that. We cannot call it as 3-bromo when we can name it as 2-bromo. By giving 2, we are reducing the number of locant or the substituent. So that's what is the rule. So substituent should be given least number in IUPAC. So we apply that. So this is 2-bromobutane. Fine. Now this 2-bromobutane, we make it react with potassium hydroxide, and this sign means heat. We heat it. Alright. So what we end up is with these two products. Alright, this is one product and this is other product. Now how do we get it? Let's try and understand. Now we have got two products. So let's work out for this first. Now see, what I have done is this, I already had explained earlier that alpha is that carbon to which functional group is attached. Here the locant Br is attached to this carbon. So this carbon becomes alpha carbon, and one beside becomes beta carbon. Alright, we are naming this as beta 1, we are naming this as beta 2. Alright, so now what happens is, for this product, I put it this way. Alright, so what I have done is, one of the H I have put it in red, and here also one of the H I have put it as red. Alright, just to differentiate. Alright, it is CH2. Instead of CH2, I have written it as CH, and one H which is going to take part in dehydrohalogenation. I have put it here. Similar here also, this is also going to take part in dehalogenation. I have put it here as red for clarity's sake. Alright, so when this product is forming, what we are finding? We are finding this to be intact. So this is CH3 intact. CH2 plus this H is CH3 intact. Alright, now so which is it which is being involved? So it is, this is the HBr which has been eliminated, which has been dehydrohalogenated. Alright, so this is HBr. So when this goes, how does it go? This bond of this H falls over here, Br takes the bond, and then Br combines with this, forms HBr. Alright, then that HBr, and this is all happening why? Because of KOH. Because KOH wants to react with it to form KBr and water. Alright, so this is, we are not showing it over here, but obviously KBr and water does form. So HBr, just assume this type of reaction, right? Acid-base reaction, acid-base reaction, but it happens from beta 1 side. To be more specific, it is this OH of KOH which is involved in this reaction. Alright, so OH minus does a nucleophilic attack on this H, and this bond falls back, forming the double bond. Br minus is with this K plus, forming KBr. Alright, so H2O formed this way, KBr formed this way. So basically what we are concerned is about the generation of this double bond. So this is how this molecule is being generated. Now when we are talking about this molecule, obviously same reaction occurs with this, forming HBr, and dehydrohalogenation occurs and giving you this molecule. So here it gives this molecule. When this is eliminated, we get this double bond over here. Alright, and then when this is eliminated, we get this double bond here. Alright, so we got, and this, if you can check it out here, CH2, H plus this H is CH2. So beta 1 is intact over here, fine, and here beta 2 is intact. Alright, so okay, understood. So that's the reason why we get two of this. Now which is major and which is minor? How can we decide? Now let's get back to Saytzeff rule. Now what does Saytzeff rule say? Saytzeff rule says that greater the number of alkyl group attached across the double bond. So we find here 4 alkyl groups attached across the double bond. So this has got more stability. Here we have got 2 plus 1 across 3. Here again there is 2 this side, and here again there is 2, but on either side. So here this is more preferred than this. Then finally the fifth one that we have, least preferred one that we have, is 1 alkyl group here. That's it. Alright, 1 alkyl group over here. So in the last one, least preferred case, we have 1 alkyl group on this side of double bond. It could be on that side also. Okay, fine. Anyways, so 4 alkyl groups across the double bond, 3 alkyl groups across the double bond, 2 alkyl group, and here it is 2 alkyl group. Now if we compare this with this, here there are both the alkyl groups are on this side. Here 1 alkyl group is this side and 1 alkyl group is this side. So across we have got 2 over here, whereas here we have got 1. So across we have more over here, whereas here we have 1. So this is more preferred than this. Alright, okay, and then this is least preferred because it's done. So I've just, for understanding, I've just given it this way. Alright, this obviously corresponds to alkyl groups. Alright, so 1, 2, 3, 4 alkyl groups across, 1, 2, 3 alkyl groups across, here 2 alkyl groups this side across, here only 1 alkyl group across, and there's only 1 alkyl group. Alright, so least preferred. I hope that part is clear. So let's get this out. So this matches with number 4. What is number 4? RCH double bond CRH. So that's what it is. We have got alkyl group here, RCH, RCH. Alright. Whereas here when we check out the fifth one is RCH2 CH. So there's we assume this to be 1 alkyl group. So it is only 1 alkyl group. This entire thing is R, right? So 1 alkyl group this side. So it is least preferred. So by applying Saytzeff rule, we can predict which of the product we expect to be major. Alright, and when this situation arises, when we have 2 beta hydrogen both having equal probability of dehydrohalogenation. Alright, so when such is the case, then via Saytzeff rule we can decide prior to formation that which would be major. So guys, this is the major product as per Saytzeff rule, and we call it as 1, 2. In second position we have got double bond, so it would be but 2E, right? Whereas in this case, in first position we have double bond, so it would be but 1E. So but 1 in, but 2 in, but 2 in is in major proportion. All right, that's one thing. Now second thing is alpha beta elimination. Now you may be aware why we call it as alpha beta elimination, because this is alpha, because this is alpha, this is beta. So in either case, in both the cases, it was alpha and beta elimination. So if you check it out here, it was, in this case it was alpha and beta elimination, in this case it was alpha and beta elimination. So in both the cases it was alpha beta elimination, so we call it as alpha beta elimination. And why dehydrohalogenation? Because it eliminated hydrogen and halogen, so dehydrohalogenation. Alright, I hope it is all very crystal clear. So do your part of story, study well, okay?